Never thought I'd see an angel, but seeing is believing. You got me believing in you.
No, we aren't rerunning the 6th television programme. This is a revision programme, and there aren't going to be any new ideas introduced in it. And since you've spent the last 12 weeks or so looking at digital and combined digital and analogue ideas, we thought it would be better to use most of the time in this programme for revising some of the analogue ideas from earlier in the course. So that's why I've got this piece of analogue equipment, this hi-fi set, set up in my office here. And you recognise this commercial equipment, the high-quality current dumping amplifier, which David Creecraft introduced to you as an example of the exploitation of the current dumping technique that you met in your home kit. And as far as this particular source is concerned, David Creecraft the other day was doing some measurements on it.
What you can see is the waveform of music which is being picked up by the pickup from a record. Now, in order to be able to design a system to work with a transducer such as this pickup, we really need to be able to characterize it in some way. And what we usually use is an equivalent circuit, such as the Thevenin equivalent circuit, which is this one. Now, this has a voltage generator and a series output impedance or internal impedance. And the other possibility is the Norton equivalent, which uses a current generator, the same value of output impedance as the Thevenin circuit, but this time it appears in shunt with the current generator. Now, in order to be able to measure the value of the voltage generator in the first circuit, the Thevenin equivalent, that's this voltage, we can do this by measuring the open circuit voltage, that is the voltage at the terminals, providing we have a device with a high enough impedance compared with the output impedance. And that's what I've got in this case. I have an oscilloscope connected across there. Okay, well now, the waveform we've seen so far is rather complicated. It's a rather complex music signal. And again, in order to be able to use these equivalent circuits effectively in circuit design, we need a simpler signal than this. And what we usually use is a sine wave. Why sine waves? Well, as we've said before in the course, we can consider most signals to consist of sets of sine waves. And in particular, you saw back in TV3 that a speech waveform can be analysed into a set of sine waves. There we showed you the spectrum on a spectrum analyzer. The horizontal scale represents frequency, and the vertical scale represents the amplitudes of the various frequency components, the various sine waves, at different frequencies in the speech waveform. So in general, we prefer to test systems and characterize systems with sine waves. But with a transducer like this, the question is, how do we get a sine wave out of it? In other words, how do we get a sine wave into it? Well, in this particular case, it's simple enough. We just arrange to record a sine wave on the record. Now, I just turn the record over to play a test track. And this track is, in fact, recorded with a sine wave, which you can now see on the oscilloscope. All right, that solves that problem. We can get sine wave excitation. Now, what we've actually been measuring is the voltage at the output terminals of the device. I've been using an oscilloscope to do this. It has a much higher impedance than the output impedance of the transducer. So the voltage I'm measuring at the terminals is virtually the open circuit voltage, which is the same as VS, the source voltage. We've measured that at a particular frequency, but we know from earlier parts of the course, Unit 8 and Unit 9 told us that that voltage also varies with frequency. So we'll need to take that into account as well in characterizing the circuit, the transducer. The other thing we need to know is the output impedance, ZS. How do we do that? Well now, in this particular case with this transducer, and this applies to many other transducers too, it's possible to turn off the internal generator. In the particular case of the pickup, all we have to do is to play a passage on the record where there's nothing recorded, so that, in other words, Vs becomes 0. And then it's simple enough to measure the input impedance of this circuit, which then tells us the value of Zs. Now, in general, it's not so easy to do that because it may not be possible to turn off the internal generator. So the other way is the method that you used in the experimental work for an earlier part of the course, where you measured the equivalent circuit of the generator, the sine wave generator, and the generator scope. The technique there is to load up the circuit with a load impedance. You used a load resistor, and that enabled you, by measuring the voltage across the output terminals and the load current, that enabled you to measure the equivalent series resistance. Well, now, let me come back to our magnetic pickup again. There's our output impedance. Now, if we weren't to do the technique I was just talking about, turning off the internal generator, how in general can we find that output impedance from a circuit where it's not possible to turn off the generator? Well, the same technique can be used as you used before with the sine wave oscillator and the generator scope, that is, apply a load and measure the output voltage. But in this case, where the internal impedance is complex, it's necessary not only to measure the output voltage, but its relative phase, and use the techniques of AC circuit analysis. And this is where phasors come in.
These two sine waves on the oscilloscope here make a good starting point to talking about phasors. The top sine wave represents the input to a linear electrical network. The bottom sine wave represents the output. You'll see that there's a difference in phase shift as well as a difference in amplitude between the two signals. This reflects the fact that the linear network contains reactive components. Now, you'll recall that sine waves have a very important property. That is, when they're transmitted by a linear electrical network, they retain their shape. As a result, when we come to do calculations on the signals and on the networks themselves, all we need concern ourselves with is the frequency, the amplitude, and the relative phase. I say relative phase because the phase angle of a given signal is always measured with respect to a reference sine wave somewhere in the circuit, normally at the input. Now, this leads to the idea that sine wave signals can be represented in the form of a diagram, a phasor diagram. The signals are plotted on a diagram of this sort in the form of a line with length proportional to signal amplitude at an angle, the phase angle, measured relative to the phase reference axis, the horizontal axis here. Now, I can use this equipment here to represent the phasor corresponding to the output signal on this oscilloscope. Well, here's the full picture showing the phasor at the top corresponding to the bottom of the two sine waves. If I vary the phase of the sine wave, you'll see the angle of the phasor changes. I'm now bringing the two waveforms back into phase. There we are, 0 phase shift, and the phasor is lying along the phase reference axis. And back, more and more phase shift out to a phase lag of 90 degrees. So here we are with a phase shift of about 45 degrees. The length of that phasor is proportional to the amplitude of the lower sine wave. And this is true at all phase angles. So phasors are used when we carry out calculations on voltage, current, and impedance in AC circuits. For example, when looking at source impedance calculations of the type that David was referring to earlier. Now, I'd like to turn our attention to a familiar circuit and look at some real voltages and some real phasors. I've chosen this one, the CR network, and I've got the circuit here with the capacitor and resistor exactly as in the circuit diagram. The input is applied across these two terminals. It's a simple circuit, but a very important one. It's frequently used to represent the equivalent source impedance of ceramic transducers. Also, is an input coupling network to a stage of amplification. Now for some phasors. This lead here is looking across the input terminals. There it is, projected along the phase reference axis. Now, the voltage across the resistor is leading the reference by roughly 45 degrees. And the voltage across the capacitor at a phase lag, again, of the order of 45 degrees. Now, Kirchhoff's laws apply to AC circuits as well as DC circuits, except that with AC circuits, we have to concern ourselves with phasors, so that the input voltage phasor is given by the phasor sum of the component phasor voltages. And we can see this now on the screen. For example, we'll start with the phasor of the resistor voltage. Let's mark that. The phasor corresponding to the capacitor voltage, we can mark that. And again, the reference phasor across the input, where the reference phasor is equal to the phasor sum of the two component voltages. Well, so far we've been looking at phase relationships at a fixed frequency, but of course in general the amplitudes and relative phases of voltages in a circuit are frequency dependent. And I want to have a look at some of these effects in this network here. I've substituted the original CR circuit for an RC circuit, and you can see the resistor and the capacitor corresponding to the components in the circuit diagram. The input is applied across these terminals here. Now let's have a look at some phasors. First of all, the reference phasor taken across the input. There it is on the screen, projected along the phase reference axis. Now, the phasor of the capacitor voltage is lagging the reference by roughly 45 degrees because we are round about the cutoff frequency of the circuit. I'm now going to increase the frequency. The signal across the capacitor will reduce in amplitude, the phasor gets shorter, and the angle is increasing towards 90 degrees. And I'm now reducing frequency, coming back to more or less where we first started. Now, I want to have another look at the input phasor. You remember that this is held at constant amplitude and at zero reference over all frequencies, while the output phasor varies in length and angle as a function of frequency. Now, because the input is fixed, the length of the output phasor tells us about the gain of the network, while the angle of the phasor tells us about the phase shift of the network. This leads to the idea of using phasors to represent the transfer function or frequency response function of the network. Now, there are several reasons why you might want to change the frequency response. For example, for equalization, you've done calculations on that type of system, and also for removing unwanted frequency components from a signal. And we've got quite a good example of that working over here. Let's have a look at it. Well, I've got a small system here which I've been looking at over the last few days, and it's producing some pretty interesting looking signals. Here it is on the oscilloscope. Now, the signal that I'm really interested in is in there somewhere, but most of what we can see is noise and interference. It's a bit of a jumble on the time domain display, so in order to try and sort out the components, I suggest we go over to a spectrum analyzer display, and we've got one here.
Well, this spectrum analyzer is a little different to the one you saw earlier. I'll start it running and see what I mean. Well, just like the other machine, it sweeps from left to right with increasing frequency. But the difference here is that it stores what it sees on the way through as it sweeps. So, horizontal scale is increasing frequency, And the vertical scale gives us the amplitude of the sine wave or frequency components. This one, in fact, is the low frequency signal that Mike wants to recover. And this one is an interfering signal. And these are some of its components. And these are all distinct sine waves. The rest of this information here is in fact wideband noise. And I should just point out that the vertical scale is logarithmic. It's about 10 decibels per centimetre, so there's something like 10 decibels difference between that amplitude and the signal we want. So the interference is quite strong. So, how do we go about recovering it? Well, the obvious thing to start with a signal in this situation, is to try to filter out all the components that we don't want. In other words, we put a low-pass filter in which will take out all the components above there. So we hope it will take out these interfering components and also all these other components. Now, these are the noise that Mike was referring to. And we know, in fact, that it goes on up to much higher frequencies. This is wideband noise. And again, this is quite a high level compared with the signal. That's about 20 decibels down, but of course covers an enormously wide bandwidth, so it represents a lot more power. So, if we had a low-pass filter, hopefully we could take out a lot of this interfering, a lot of these interfering signals. So, Mike?
Yes, well, I've patched up a low-pass filter on the analog module here. You'll recognize your HomeKit module. And let's have a look at the effect of a low-pass filter. Take the signal into the input of the filter and transfer the probe to the output of the filter.
Okay, well, there's another useful thing we can do with this spectrum analyzer. I can save the spectrum I've already displayed and draw a new one so we can compare the two. So let's do that. I'll switch over and start again. Well, now you can see the effect of the low-pass filter. It's attenuating the higher frequency noise components. The higher the frequency we get, the more attenuation we get. But it's still leaving the interfering signal fairly strong. It's attenuating it quite a bit, but it's still quite a high level compared with the signal that we want.
Well, if you look at the time domain waveform, you can see the residual effect of that high frequency interference putting the ripple on the waveform. There's one way we can get rid of that. We know what the interference frequency is because we've been able to measure it from the spectrum analyzer. So I've designed a notch filter, which is a very, very sharply tuned filter, right at the interference frequency. The idea is to simply notch it out altogether, or at least to considerably suppress it, and bring it down to a level where we can consider it to be negligible. So let's try the effect of that. I've got the notch filter built up on the patchboard here. That's the signal going to the input of the notch filter, and we'll straight away look at the spectrum at the output from the notch filter.
Okay, we'll draw the spectrum again. Here we go. And now we're beginning to see the effect of the notch. There's a notch in the response, just there, and then we level out again. In other words, this filter isn't attenuating the high frequency noise very much, but it is putting a notch in there, which is attenuating the interfering signal. And as far as we can tell from the spectrum, it's gone completely. I wonder what the waveform looks like.
Well, we've got the residual high-frequency noise obscuring the waveform, although I must say there's no real sign of that ripple which was there due to the interference. So, I think the best way to finish is to put all of the filters in a row. We'll start with the signal, into the low-pass filter, through the notch, and then we'll look at the final output of the whole lot together. So, signal into the low-pass filter into the notch, and again we'll have a look at the total spectrum.
Well, now you can see the dramatic effect that the two filters have. The low-pass filter is taking out all the high-frequency noise, and the notch is suppressing the interfering signal, so we should get a dramatic improvement. In fact, we're now attenuating the high-frequency noise by about 40 decibels. And the bit of noise that's left is, in fact, residual noise in the spectrum analyzer itself. we can't filter much nearer to the signal than that without starting to attenuate the signal. And in fact, it wouldn't make very much difference because the noise goes on up to much higher frequencies. So we've taken out quite a lot of bandwidth compared with this little bit just here. So the reduction in noise power is quite significant, and the difference we would make by adding that little bit in as well is neither here nor there.
Well, it's beginning to look pretty respectable now. It's looking almost like a sine wave. You can see a bit of low-frequency noise still perturbing the signal, and we could get rid of that by putting in some high-pass filtering right down at the bottom end to block out some of the low-frequency noise components. But we shan't be doing that for the moment. However, I think you'll agree that by doing a bit of signal conditioning, you can certainly make a big difference to a signal. And just to remind you, let's go back to where we came in.
Well, that was a brief look at equivalent circuits and analog signal processing. Now, we could equally well have talked about purely digital signal processing, as happens, for example, in this calculator, where we have a keyboard, internally digital circuits, and a display. And the corresponding equivalent systems diagram for that would be something like this, where we have keyboard, digital signal processing, and display. But more generally, we might expect to find some combination of analog and digital techniques, as we talked about in units 12, 13, and 14, and in the 9th television program, which went along with those units. Remember there the printing press, which we talked about, and here is the system diagram you saw in that program. It looks fairly complicated at first sight, but if we look carefully, we can see the various sections. For example, there are analog inputs here derived from the inking ducts, analog to digital conversion, and digital inputs from a keyboard and from a cassette drive and a display system, all combine various interfaces to a digital bus, a digital memory, processors and so on, which provide information to the logic circuits which drive the inking keys. So in this system, we have both analog and digital methods combined, and a general electronic system might well be described in this sort of way, with analog and digital inputs, a general signal processing unit which uses both analog and digital methods, and analog and digital outputs. And a further example of this sort of technique is provided by the instrumentation system you saw in the previous television program. The analog measurements on something like this hi-fi amplifier were done using an instrumentation system controlled from a desktop computer and using the general interface bus that you saw in that program. So the message I'd like you to take away is that analog and digital methods should not be thought of as separate alternatives, but they should be used wherever appropriate. We separated them to some extent in the course for clarity and ease of teaching, but in modern electronic design, they should be thought of as complementary.